Hello everyone, myself Pooja MC, first year MSc Chemistry, JSS College of Arts, Commerce and Science, Ooty Road, Mysore. Today I am going to present a seminar about a topic, the electromagnetic spectrum, in that meaning and spectral regions and emphasis on general components of an absorption experiment. In that contains electromagnetic spectrum, in that meaning and regions of spectrum. The regions of spectrum are gamma rays, X-rays, UV visible, infrared, microwave and radio waves, and general components of an absorption experiment, in that the source, absorption cell, dispersing element and detector and reference. The electromagnetic spectrum. First of all, we will know the definition of spectroscopy. The spectroscopy is the study of interaction between matter and electromagnetic radiation as the function of wavelength or frequency of the radiation. The electromagnetic spectrum consists of different types of electromagnetic radiations that are arranged in order of their increasing wavelengths or decreasing their frequencies. In vacuum, all electromagnetic radiation travels at speed the speed of light c, that is 3 into 10 to the power of 8 meter per second, and frequency v, both conventionally in a vacuum. The spectral regions. The electromagnetic radiations are arranged in order of their increasing order of wavelength or completely decreasing frequency. A complete spectrum is obtained. The spectrum can be divided into according to energy or wavelength. The name of the region, wavelength, here are the some of the spectral regions. Gamma rays, X-rays, for UV, near UV, visible, near infrared, mid infrared, far infrared, and microwave and radio wave. These are the electromagnetic spectrum regions, and we can see here the gamma rays have the less wavelength and as compared to X-rays, ultraviolet rays, infrared, microwave and radio waves. The regions of the electromagnetic spectrum, in that radio waves region, they comes under the range of frequency 10 to the power of 6 to 10 to the power of 10, and the wavelength of 10 to the 10 meter to 1 centimeter. And these radiations are observed in the NMR spectroscopy. And the microwave region, these microwave region radiations are observed in the rotational spectroscopy. And infrared region, these radiations are observed in the vibrational spectroscopy. And the visible region, these visible radiations are observed in the electronic spectroscopy. And also ultraviolet region, these radiations also seen in the electronic spectroscopy. Next, gamma rays. The wavelength of gamma rays lies in the range of 0.001 to 0.01 nanometer, which is carrying the highest energy photons. They are similar to X-rays, distinguished only by that they are emitted from excited nucleus. The disadvantages of gamma rays cause ionization of the medium and affect the biological system and living organisms by damaging cells. Next, X-rays. The wavelength of X-rays lies in the range of 0.01 to nanometer. The most useful portion of X-ray region for chemical analysis lies between 0.07 to 0.02 nanometer. X-rays are used in spectroscopic technique, which is either called electronic spectroscopy or for chemical analysis, that is ESSEA. X-rays may cause different types of molecular damages in living system and biomolecule, which may cause mutation and cancer. Next, ultraviolet and visible red. The total wavelength of ultraviolet region is 10 to 400 nanometer. The higher energy side of UV region is called vacuum, that is far ultraviolet, lies in the wavelength of range 10 to 200 nanometer, while lower energy side of UV region is called near UV and its wavelength range is 200 to 400 nanometer. The advantages of ultraviolet and radiations are it stimulates the production of vitamin D, which helps to vitalize bones, muscles, and immune system. The disadvantages of UV region is skin damages, wrinkles, sunburns may cause a skin cancer. Here we can see the sunlight stimulates the production of vitamin D, which promotes formation of healthy bones, and also the ultraviolet region. The more exposure to ultraviolet radiations causes skin damages, and these ultraviolet radiations uh, are protected by the ozone. Next comes the visible region. The The visible spectral region lies in the wavelength range of 400 to 800 nanometer. Several natural phenomena occur in the visible region of radiation. Advantages of visible region are the visible light helps to humans to see. Photosynthesis become possible in this range as a single molecule of chlorophyll is excited by a single photon. Here we can see the formation of rainbow is due to the visible region light. Next, the complementary colors. When a particular wavelength of light is observed, the complementary color is transmitted and gives the color to the object. The, the color of tomato which we see red is due to the color of green. Infrared radiation. The wavelength of infrared radiation region is lies in the range of 0.57 to 500 micrometer. We use infrared radiation in many ways. The advantages of these infrared radiations are used in thermal imaging cameras, remote controls, and also infrared therapy has many roles in the human body, which includes detoxification, pain relief, boosting of the immune system, and lowering blood pressure. The disadvantages of these infrared radiations are prolonged exposure to higher radiation leads to lens, cornea, and retina damage, including corneal ulcers and retinal burns. Next, microwave radiations. These are the forms of electromagnetic radiations with wavelength at 0.3 millimeter to 0.5 meter. The prefix micro is not meant as wavelength in micrometer range. It indicates that microwaves are small compared to waves used in typical radio broadcasting. The advantages of these microwave radiations are these radiations are used in microwave oven for quick eating or preheating. Microwave sensors have higher sensitivity and hence they can detect non-human presence such as animals, fast-moving objects in the air, etc. The disadvantages of these microwave radiations are through microwave cooking leads to dehydration as the water content decreases. Exposure to high level of microwave can cause skin burns. Here we can see how microwave sensors works. Next, the radio waves. These radio waves is an electromagnetic wave that is range from extending from 3 kHz to 300 GHz, which include those frequencies used for communication or radar signals. Radio waves are transmitted easily through air. They do not cause damage if observed by human body, and they can be reflected and refracted to their direction. Next, the general components of an absorption experiment. Absorption spectroscopy frequently used in all the regions of the spectrum. The electromagnetic radiation of a specified wavelength range passes from a source through a sample containing compound of interest, resulting in an absorption. Here we can see how the absorption experiment works. Here is the source present and the source of light enters through entrance slit. This slit is monochromatic and enters to absorption cell which contains the compound of interest, and next to dispersing element. This dispersing element splits the light into compound light into different colors, and the uh, move enters through exit slit of monochromatic and to detector, and the absorbency is in the display. Next, the four main components of an absorption spectroscopy are source, dispersing element, and detector. The source. It is an ideally continuum in which radiation is emitted over a wide range with uniform intensity. Next, the absorption cell. It contains the sample must have windows made from a material which transmits the radiation. It also be long enough for the absorbance to be sufficiently high. In high resolution spectroscopy, the sample is in the gas phase at a pressure which is sufficiently low to avoid pressure broadening. In liquid phase, all rotational structure is lost and vibrational structure is considerably broadened, but it is important. In the solid phase, in which the sample may be a pure crystal, mixed crystal, or solid solution in a frozen noble gas, rotational motion is quenched as the molecules are held rigidly. Next, the dispersing elements. Dispersing element splits up the radiation into its component of wavelength. Dispersing elements are in prism, diffracting grating, or interferometer, but microwave and millimeter wave spectroscopy do not require such an element. Next, prism. Prism as a dispersing element, they have been largely suspended by diffraction grating and interferometers. If wavelength lambda and lambda plus d lambda are just observed separately, then here we can see the lambda and the d lambda plus d lambda. Our corresponding frequency interval dB is the resolution obtained. Here we can see how the prism splits the light into its components of wavelength. The ray passes from the lens 1 and enters through a prism and diffract into components of wavelength. Here we can see lambda and lambda plus d lambda are the wavelengths. The resolving power R of a dispersing element is defined as R is equal to lambda divided by d lambda, or which is equal to V mu by d mu. Here mu is the frequency and lambda is the wavelength. And for a prism, R is equal to, that is resolution, resolving power is equal to dn by d lambda into b. Here n is the refractive index of the prism. For high resolving power, dn by d lambda should be large, and b is the base length of the prism. Next, diffraction grating. It consists of a series of parallel grooves grooved on a hard glassy or metallic material. The grooves are extremely close spaced, a spacing order of 1 micrometer. Gratings are coated on the ruled surface with a reflecting material, such as aluminium, so that grating also acts as a mirror. The below figure shows how light falling at 90 degrees to the surface of a reflecting grating G is dispersed. It is the diffracting grating and G is the reflection grating. And here we can see how the dispersion of element components of light is splits into its wavelengths. And here m lambda is equal to d into sin I plus sin theta. It is the general equation for a diffraction by a grating, and where I and theta are the angle of incidence and reflection respectively. T is the groove spacing, lambda is the wavelength, and m is equal to 0.2310123, the order of diffraction. Next, the last is detectors, and most important one is the detectors. The detectors must be sensitive to the radiation falling on it, and the spectrum is very often displayed on a chart recorder. The spectrum may be a plot of absorbance or percentage transmittance as a function of frequency or wave number displayed on linearly along the chart paper. Here is the elements of an absorption experiment. Absorption on the various regions of the spectrum. Here are the region. The first is microwave region. The source used in microwave region is backward wave oscillator, and the absorption cell is mica, and the here we doesn't use any mic dispersing element, and the detector used is crystal diode. Next is far infrared. Here the source used is mercury arc, and the absorption cell used in polymer, and the dispersing element may be grating or interferometers, and the detectors used here are cell, thermocouple, bolometer. Next, the mid and infrared radiation. In that region, we use the source, nuanced filament or glow bar, and the absorption cell is NaCl or KBr solutions, and the dispersing element is grating or interferometers. The detectors use the cell, thermocouple bolometer, photoconductive semiconductors. And next, the visible region. Here, the source used is tungsten filament, and the absorption cell is glass, and the dispersing element used are prism, grating, interferometers, and the detectors used are photomultiplier, photodiode. Next, the near ultraviolet. The source used in deuterium discharge lamps, and the absorption cell used is quartz, and the dispersing elements are prism, grating, interferometers, and the detectors used are photomultiplier, photodiode. And the last is for ultraviolet region. In this region, we use micro discharge in noble gas, and the absorption cell is lithium fluoride, and the dispersing element used is gratings, and the detectors used are photomultiplier, photodiode, etc. Here I referred these two books for this prepare seminar, and the first is Modern Spectroscopy. The author was J. Michael Hollas, fourth edition, and the page number is 40 to 47. And the second one is Organic Molecular Spectroscopy. The author was Ajay Kumar Manna, and the page number from 3 to 5. Thank you.